Hey there, and welcome. We hear about environmental pollution all the time, but have you ever really stopped to think about how a polluted river or smog in the air actually affects your health? Well, today we're going to dig into that. We'll trace the journey of toxins from the environment straight into our bodies and see what the consequences really are.
That's a great question, right? It really gets to the heart of environmental science. The answer isn't simple. It's more like a complex chain of events, kind of like dominoes falling one after another. It all starts with pollution and ends with a direct hit on our health. So let's follow that chain and see exactly where it leads.
And this right here is the core idea we're going to unpack today. Environmental damage isn't some abstract thing happening out there. It's not. There's a direct line to our health, and really getting that connection is step one.
Okay, so with any problem, you've got to figure out the cause first, right? So let's put on our detective hats. First up, we're identifying the primary culprits, what we'll call the agents of harm.
For most of human history, our biggest health threats from the environment were biological. Think things like bacteria in the water that caused cholera or parasites causing malaria. Those were the big ones. But now with industry and modern farming, we're up against a whole new set of threats, chemical agents.
And here's a look at some of the main offenders. We've got heavy metals like lead and mercury, which, can really mess with the nervous system. You find them in everything from old paint to industrial runoff. Then you have industrial byproducts like dioxins and stubborn pesticides like DDT that can stick around in the environment for decades. And then there's this really sneaky category called endocrine disruptors, which can mess with our hormones.
All right, so knowing who the culprits are is a great start. But now we need to understand how they do what they do, their methods, if you will. So how do these toxins actually build up in the world and in our bodies to cause all this trouble? Let's dig in.
This leads us to a really important idea called biomagnification. And this is the key to understanding how even a tiny bit of pollution can end up having these huge, devastating effects. Simply put, it's how toxins get more and more concentrated as they travel up the food chain.
Okay, so here's how it works. Just imagine a toxin, say mercury, gets into a lake. Tiny little organisms like plankton absorb a little bit of it. Then small fish come along and eat thousands of those plankton, and all that mercury builds up inside them. Then a bigger fish eats hundreds of those small fish. So by the time you get to the top of the food chain, an eagle, or even us eating that fish, that toxin has become super concentrated to a level that can be really dangerous.
And this isn't just some theory, it happens in the real world. The classic example is the pesticide DDT. It got washed into rivers and lakes, and as it moved up the food chain, it just got more and more potent. By the time it reached predators like bald eagles, the DDT levels were so high that it messed with their ability to make strong eggshells, which caused their populations to just plummet.
Okay, so there's another really tricky way these toxins can get to us, and that's through what's called endocrine disruption. So think of your hormones like little keys. They fit into specific locks on your cells to kick off all sorts of important stuff, like growth and development. Well, endocrine disruptors are like fake keys. They can fit into those same locks, either blocking the real key or turning the lock when they shouldn't. And it just sends a whole cascade of wrong signals all through your body. A real mess.
So this number, 50%, on its own, it's pretty stark. And it points to a really concerning trend in human health that scientists are working hard to figure out.
What this is about is the fact that since the 1940s, average sperm counts in men have dropped by about half. Now, the cause is definitely complex, but many scientists think that our constant exposure to these endocrine-disrupting chemicals is a big part of the story. And that, as you can imagine, has huge implications, not just for individuals, but for entire populations.
And something that's super important to remember is that these chemicals almost never act alone. That's where something called the synergy effect comes in. It's this idea that when you mix two chemicals, the combined effect isn't just 1 + 1 = 2, it can be exponential. 20 + 20 doesn't just equal 40, it can equal something crazy like 400. The danger just multiplies.
Okay, so we know who the bad guys are, and we know how they work. But how do scientists figure out just how bad they are? How do they measure the impact? So next up, let's look at how they gather the evidence to figure out how dangerous a substance really is.
And the main tool they use for this is something called the dose-response curve. It's basically a graph that shows a concept that, kind of makes sense. The more you're exposed to something, that's the dose. The bigger the effect, that's the response. Scientists use this to map out just how toxic a chemical is.
So, using these curves, scientists can pinpoint some really key numbers. First, there's the LD50. That stands for lethal dose 50. It's the amount of a substance that's fatal to half of the animals in a test group. But of course, not everything that's bad for you is lethal, right? So they also look at the ED50, or effective dose 50. That's the dose that causes some other significant problem, like organ damage, in half the group. And these numbers are absolutely crucial for setting safety limits for, well, for everything.
All right, so we've got the science down. We have the tools to measure risk, but how do we actually use that information to make decisions as a society and for ourselves? And maybe more importantly, why do our own gut feelings about what's risky so often clash with the actual science? That brings us to our final section, where science meets psychology.
When it comes to the official process, government agencies use a really logical four-step system. Step 1. Identify the hazard. What's the chemical? Step 2. Do that dose-response assessment we just talked about. Step 3. Figure out how much people are actually exposed to it. And finally, Step 4. Put it all together to characterize the risk. It's all very systematic.
But if the process is so logical, why do we, as people, often seem to fear the wrong things? Why are we sometimes terrified of something with a tiny statistical risk, but will totally ignore something that's way, way more dangerous?
Check out this number, 1.8 million. It's a huge number, and it perfectly shows this massive gap between scientific risk and how we feel about risk.
So what is this number all about? Well, it gets into some really fascinating psychology. Basically, a person is 1.8 million times more likely to get cancer from smoking than from drinking tap water. And yet, how many people do you see smoking while drinking bottled water to be safe? So what gives? A lot of it comes down to control. We tend to freak out about risks that feel forced on us, but we're way more chill about the risks we choose to take. Wow! Okay, we have covered a ton of ground today. So, to wrap this all up and make sure it sticks, let's do a quick recap of the key ideas you'll definitely want to remember. All right, here's your study guide, the absolute essentials. Remember biomagnification. That's how toxins get stronger as they go up the food chain. Then you've got endocrine disruptors. Those are the false keys messing with our hormones. Don't forget the dose-response curve in LD50. That's how we measure how toxic something is. And finally, remember those 4 steps of risk assessment and just how different it can be from our own perception of risk.
And that's a wrap on our deep dive into environmental toxins. So I'll leave you with this question. Now that you know all this, how risk is scientifically measured versus how we often feel it, what's one risk you'll think about differently today?